Okay, let us begin. I think everything should be in order. Screen share, that's camera. Yes, cool. Okay, so polynomials. This class will be basically focused on effectively revising at least all the key concepts of polynomials and then how we can apply them to sketching, solving, that sort of thing. So the first kind of thing we need to understand with polynomials is that they're pretty useless unless they're factorized. There's not a whole lot you can do with a polynomial when it's in its extended polynomial form. And so a lot of what we have to do when working with polynomials is do something to factorize them. And so one of the things we look at to achieve that for things that are higher than quadratics is the polynomial division, essentially. So if we know a factor ahead of time, if we use our remainder or factor theorems, for example, to achieve one of the possible factors, then one of the things we can do to help factorize a polynomial is to do it through polynomial division. And so polynomial division is a bit of an iterative process. You repeat an algorithm multiple times until you get it down to its until it's completed its full number of loops. This would actually be a decent question for pseudocode, but it just doesn't seem to show up, oddly enough. We did a bit of a masterclass on that before, and a lot of it was basically just Newton's method over and over again. This would be a good one for it, but anyway. So, the first of the basic examples is we have some sort of cubic. We know that x plus 2 is a factor of that cubic. And so if you go through the polynomial division phase, what you'll essentially do is have split this up into two factors, x plus 2, and then some other quadratic that multiply together to give that cubic. Top is going to be called n of x, the bottom is going to be called d of x, n for numerator, d for denominator. So you set them up like this, and what you do by starting out is looking at the two highest order terms, or the highest degree terms, I should say. Order, degree, they mean the same thing. Good idea to write your polynomials in descending order. That way it becomes a lot easier to figure out which one's which, or which ones you should be looking at any given time. So in this case, we have x cubed and x. The first thing we do is divide the inner one by the outer one. X cubed divided by x, x squared. We chuck that result on the top. So you'll be able to do this in your head and then put it on the top. If you want, you can save some space on the outside of your, like on the margins, for example, to write out those equations, because they might get a bit complicated. Not necessarily the division portion, more so perhaps the multiplication portion, where you've now got to grab that result that you just achieved and then multiply through the entire denominator. So that's what this is. You grab this thing in blue, multiply by the whole thing in red. As you get more confident with this, you're able to do this stuff in your head fairly chill, but if you're revising this or learning it for the first time, for anyone in the recording, you can, again, draw these or write out these work solutions, or write out your working in the margins. We're going to pop that answer directly underneath the inner thing. From there, we perform a subtraction. So it's the top minus the bottom. Now, you need to minus the entire bottom. That's why when I do it, I'll typically put brackets around the thing to really emphasize, hey, you're not just putting a negative sign on this thing, you're also putting a negative sign on this thing. That's where this will be especially handy if you're doing work in the margins, because this is algebra that we're all used to, right? This thing minus this thing, that is written in a way where you're dead set used to that thing. Whereas when it's like this, presented in a different order, it may not be as obvious what's going on there. This is obviously a lot more condensed, so if you can do this, it'd be better, a bit faster, but yeah. So always just top take bottom. So x cubed minus x cubed, 0. X squared minus 2x squared minus x squared. There's a whole bunch of zeros here, so these are just going to keep their value. Then we just repeat those steps in order until we've basically got this down to nothing. So you do our division of the new biggest term by the biggest term of the denominator. So that's going to be this and that one, giving you negative x. Multiply, subtract, divide, multiply, subtract, divide, multiply, subtract. Do you want me to show those in any more detail? You're happy enough with the repetitive nature of that?
I was doing it as you were going on, and yeah,
Oh,
it's all
sure.
good. I've gotten it.
You got it? Okay, fine.
Yeah.
Yeah, so if when done right, this will equal 0. Now I should clarify what I mean by done right. When you're dividing by a factor, if you know it's a factor ahead of time, you should get 0. If there's any remainder, then what that means is you either did not actually start with a factor or you've done something in this process incorrectly. One of the two things is true. So as far as troubleshooting things, you probably would have started with like a remainder or factor theorem type thing. Double check that you've done remainder factor theorem correct. Then once you double check that, have a look and see, okay, maybe I've done something messed up in here, because you should always get 0 if you've chosen a factor. The result up top is the second factor of that polynomial. So basically what you have is, was that a question, sorry?
No, and then you like I got that as well. Now I just simplified it further into its two factors as well.
Yeah, yeah.
Yeah.
And so I guess just to like expand on why that's factorized it, what you've essentially done is write this equation here. This divided by this equals that. And so all we're really doing is multiplying both sides of the equation by x plus 2 there. That's giving you the polynomial that you started with. This is a factor, and then this is a factor. And in doing so, you've just created a null factorable situation, which I may or may not have at the bottom here. I do not have at the bottom there. You can see if you do have a remainder, it's not going to work, right? There's no null factor law here anymore. Or I guess there kind of is, but like that's one of your factors, and that's not great. But okay, cool. So that's polynomial division. As far as how you even get the factor to begin with, that's your remainder and factor theorem. They mean the exact same thing. Factor theorem just means the remainder is 0, as we explored earlier. So to do remainder theorem or factor theorem, it's always f of x, so the polynomial that you're trying to divide, f of negative b over a, where the b and the a come from the linear that you're either testing to see if it is a factor, or already know that this is the thing you want to test ahead of time. So if you're simply just trying to find remainder of polynomial after division by some linear, just, there's your b, there's your a, chuck it in, and simplify. That gives you remainder. We want to get remainder of 0. That's our goal. So if we want to prove that we have a factor, we want to get remainder 0. Now, that's about proving a factor ahead of time. We already know what that is. If you need to now find a factor, there's two circumstances that come up. The most common one is going to be where you have a monic polynomial, which I'm pretty sure I've used the term correctly. Basically means there's no coefficient on the x cubed, or I guess more accurately, the coefficient on the x cubed is 1. This is where all you have to do is label the factor pairs of the last term, the constant. So, you're going to have your plus minus 1 and 6 and plus minus 2 and 3. Both of those pairs are going to multiply up to give 6. All of these are the integers that you're going to test subbing into f of x. If you get 0, you're happy. You found a good number. If you don't get 0, you're not so happy. Try another one. Now, typically speaking, you want to start with the easiest things to plug in and then work your way up to the hardest things to plug in. Not only because that's less work for you to do, but it's also because that's what the assessors are probably going to be choosing their numbers based on. Like if they're choosing any of plus or minus 6 as their factor, they just were very negligent in their assessment. That, or they're giving you like 10 marks to do the thing because it's going to take you about 10 minutes to test all these bloody factors, especially if you don't get tech free. I mean, there really is no tech active equivalent of these because there's just the CAS, and then you can do factor. You can just force the CAS to factorize your polynomial. So this stuff really only is valid for tech free. In saying that, I'm sure there's going to be one example that's going to come up very niche that might require you to do this rather than the CAS, but most circumstances it's going to be a tech-free thing. So okay, we've tested our integer. What's going on here? What do we do with that integer? Well, what we can essentially say is, okay, if f of 1 equals 0, and factor theorem means f of negative b over a equals 0, then basically what I can say is, cool, let's just make 1 the same thing as negative b over a. And because our polynomial started with no coefficient on the x cubed, the coefficient is 1, we actually take a to be 1. Now, there's a whole proper proof and rationale as to why you can do that. We're just going to take this for granted. There's a lot more math that goes involved into that. Point is, if you see that you have a coefficient of 1 on your leading term, you set a equals 1. That's just the assumption there. And so that just gives you 1 equals negative b, or b equals negative 1. You now have the a and b term of your linear, and then you continue on as per how you would do through a polynomial division on that. Is that all fair enough?
Oh yeah.
Sweet. This is what I was looking for as the as the final thing. It's in the remainder of factor theorem section. This is what I was saying about how you can multiply both sides of the equation, and then because you're trying to find usually the roots of the polynomial, you set obviously the right-hand side equal to 0, and then null factor law your way through all of that. Cool. Now, it's not just useful for solving polynomials, it's also useful for sketching polynomials. So what you'll find with cubics and above, actually, is that there's a lot of different ways you can sketch them depending on what kinds of factors you have. So if you have a factorized cubic or a factorized quartic or a factorized whatever, there's a few key things you have to look out for. Namely, the sign of the x cubed term, whether it's a linear or a repeated linear. Those will tell you different things based on the graph. So if we have only linear factors and it's overall net positive, here's what's going on. So we've got a sequence of 3 linear factors. Any linear factor solution via null factor law is going to give you the x-intercepts of that function. Plain and simple. Y-intercept is always x equals 0. It doesn't matter if it's factorized or not. In fact, it's easier if it's not factorized, because then it's just going to be whatever the plus d all the way at the very end is. As for overall shape, we need to know if it's positive or negative cubic. You're essentially just going to do a quick sign analysis on the x terms. So you count the number of positive x's, the number of negative x's, and you can make a determinant based on that. We got positive, 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 so that's going to be a net positive. That's fairly chill. If there's ever a mismatch between them, then you're going to go with negative. But okay, so for positive, it means we're starting bottom left and ending top right. So what that ends up meaning is that, roughly speaking. So you do your bottom left, you draw out your 3 x-intercepts we had from earlier, and you turn wherever feels good. Without calculus, you're not going to find these turning points, at least not through the null factor law, the factorized version. And tech-free, the mathematics required to find those turning points is pretty nasty. It'll, is it going to be here? Yeah, okay. So you take your factorized cubic, expand it all the way out so you don't have to do 2 separate product laws, then derivative, make it equal 0, factorize again, find your values, sub back into f. It's a whole ordeal. They just don't get you to do this. But you could if you needed to. Fair enough?
Yeah, I mean, I guess for anything to find turning points, we just do derivative equal to 0.
Yeah. For the vast majority of cases, derivative 0 is your bread and butter way of finding turning points. Quadratics, you can use axis symmetry if you want to. Even with quadratics, I was pretty much dead set on just using derivative 0 as everything. Even better could be f min, f max for CAS stuff specifically, because I didn't actually know what those functions were when I graduated in school. by the way. So if you see some of the things where I'm using derivative 0 where I could have used fmin, fmax, it's because I was actually using them before I looked. I wrote that before I looked into the CAS as to what it could actually do.
Okay.
So a lot of the time fmin, fmax will be a lot nicer, or at least a faster approach. Now that obviously comes with the caveat that you should know derivative 0. Like, you need that for tech free. And so if you had to do one or the other, definitely derivative 0, because if you don't remember that one, you won't be able to do it tech free.
Yeah.
Here's an example. If you have a negative cubic, right, you got one negative x, two positive x's. When you do the sign analysis on that, you've got an imbalance, right? And so that just means everything else is going to be the same, except for the fact that it starts top left, ends bottom right.
Yeah.
If you have repeated linear factors, that means you have a linear squared. That's where you still get x-intercepts out of that null factor law, but the solution to the repeated linear is now a turning point. That's the only thing that changes. That, and when you're counting x's, this one now counts twice. So you've got an x here and another x in the same spot. Positive, so starts bottom left, ends top right, but you can see now that we actually turn on x equals 2. So I guess that's one way where you can get an easy turning point. This one you're still not getting at all, though. The bit of a painful part of trying to sketch this tech-free is, like, where do I draw this turning point? Because, like, presumably one way I could do it tech-free would be to draw it going up through 8 and then turn down, or I could go up, down through 8 and then turn. Without, like, having a CAS on hand, it can be kind of difficult to know which one to do. Most of the time, the graph is chosen in such a way where it's very hard for you to draw it like that. Like, it feels pretty unnatural to draw quite a steep cubic and then come down quite rapidly. So having a decent sense of scale can help with that. But you're also just not going to get graded poorly if you accidentally put it over here instead, because without calculus, you're not going to actually figure that out.
Yeah, fair enough.
This is a topic taught way before calculus, so it's not expected knowledge for it. Here's the exact same example, but we got a negative, so that's one negative, two positive x's, again, as before. If there's a negative in here, it doesn't actually count for anything because it's now double negative, so it cancels itself out. So you won't ever really see that. What you may see is a negative, like, on the outside of the entire cubic, like on that, like, left at the very front of it. That also counts. So same shit, but this time it's going to be top left and ending at bottom right instead. And this one's exceptionally nasty because now you've got a turning point, which, may be at x equals 0, but it could be slightly left or slightly right of that. It's hard to say. If you have a quadratic factor, that gets even weirder, especially one that has no solutions, right? X squared plus 1, that's got no solutions. It does just mean you have one x-intercept. That's fine. It is a negative cubic, at least in this case, so that's also fine. What's less fine is how you actually do this shape. That is not a stationary point of inflection, like you have for the regular inflection point form cubic. That is a normal, just some other inflection point. The rule I have around this is just do some wobble at some point along the graph and call it a day. That's the best you can really do in this circumstance without having access to calculus or other exceptionally extensive methods by which you could figure it out.
Okay.
So, there's a few things that are a bit weird there. As long as you, look, you're going to get the mark. As long as you start top left, end bottom right, and only intercept at the spots where you know there are intercepts, then mostly you'll be fine. We already briefly had a look at this. That's sketching. Cool. Just to go slightly deeper into that, if you have anything more absurd, like this is, what's this, 4, 5, this is a power of 9 polynomial, the real rule for, like, linear or repeated linear is as follows. Linear is still x-intercepts. Where you get into repeated linear, you can actually split them between whether they're even or odd power linear. Now, when I say odd, I mean anything from 3 up, because technically power 1 would now make that linear again. So even power are just going to be a bunch of turning points. We saw that earlier. It was like a linear squared. Same thing if it's a linear to the power of 4 or power of 6. Any of those will still be turning points. Odd are going to be inflection points, specifically stationary points of inflection. We kind of already know this from the inflection point form of the cubic. We're just sort of formalizing that here. So you can see we have an odd power term here, we have an even power term here, we have an x-intercept, and so when all is said and done, we inflect there, we turn, we inflect there, we turn here, and we cut here. And so in that way, you can still get a rough estimate. Now that's just those key features that we found. How do we get the rest of the shape? Well, that's going to come from... Oh, I actually counted this wrong, sorry. This is a power of 10, not a power of 9. You count the overall power of the graph. Power of 10, even, it's going to be a quadratic type shape, which means it's either going to start and end top or start and end at the bottom, like a parabola would.
And like as an even power increases, does that mean like when it goes up, right? There's like the far like lines, like they become steeper, right?
Oh yes, much steeper. Like there's a reason I didn't put an axes on this. That is negative 625.
Yeah.
This is huge.
Yeah.
Yeah, this is massive. And so yeah, big powers are going to make these dramatically bigger, but as you can see, you obviously don't really care too much about that. You're just drawing the shape and then putting the numbers to associate with that shape. Because we know it's power of 10, it's quadratic-like, so it's going to have the kind of parabola shape on the outskirts, and then from there you can then just sort of draw what makes sense. It's got to inflect here, so you do a quick wobble. It's got to cut through a y-intercept down there. For it to then cut through an axis intercept, you've definitely got to turn at this spot. That should make sense. And then to then turn here, you've obviously got to turn somewhere in the middle of this. So even without getting this perfect exact shape, you'll get, roughly speaking, what it'd be. Like maybe you draw a smaller turning point here, maybe it's a bigger one. It's whatever. You're getting the shape right.
Yeah.
This, by the way, is absurd. The book has never gone above 4. So this was just to demonstrate a point. Yeah. Cool. All right. So that's pretty much everything there as far as a crash course on that sort of stuff. You are the only one in the class. I did pull up 4D because I felt like this was more of the stuff you're interested in for the unit 3-4. I'm curious if you have anything else you'd rather be focusing on. Maybe just like have a scan of what's in here and see if this is the kind of stuff you were looking to really like focus on.
Yeah, I'll have a look real quick. I feel like the questions like 8 to 10, those questions I'm like that's probably like what I usually struggle in.
Oh, sure, okay. Yeah. Prove divisible by that. Okay, so maybe even before then. So something like from 6 to 10, perhaps. These also give me the same sort of vibe.
7 is like 7 doesn't have any variables in
Yeah,
it. Like
7's got no K in it. This one's got an A. Yeah, okay. Fair enough. So it's when yeah, prove it's divisible for all values of K. Find value of K for certain things. Yeah, so it's still going to be the overall same process. You're still going to say, okay, cool. I've seen keyword divisible, so I'm going to use factor theorem. I've seen keyword remainder, I'm going to use remainder theorem. The starting point is overall going to be the same. So if we look at, yeah, so I guess from 8, you want to have a look at 8?
sure.
Cool. Prove that cubic is divisible by x plus 1 for all values of K. So effectively saying, doesn't actually matter what k is, x plus 1 should always be a factor of this polynomial. So keyword divisible, what are we expecting as some sort of approach for this?
Like factors.
Yep, trying to get the factor, absolutely. And how are we going to do that?
Factor theorem.
Factor theorem, absolutely. So how are we going to apply a factor theorem to this?
Well, we do negative b over a, and negative b is -1, and then a is just 1. So we sub -1 into the equation. Into f, sorry.
Yeah, -1 into f, that's good. Yep, f of -1, and so obviously we're just going to put a -1 in all the spots in that polynomial. So we're going to have -1 cubed, which is just -1. Then we're going to have k plus 1 multiplied by x squared, which is just going to be 1. Then we're going to have k plus 9 multiplied by x, which is of course just 1 once again. Oh, sorry, -1. Let's fix that. And -7 at the end. Cool. So that's f of -1 equals all of that. Simplifying is fairly chill here. -1 plus k plus 1 minus k minus 9 minus 7. You can see the k's are going to cancel out. -1 plus 1 also cancels out. And then -9 minus 7 you've got. Okay, I've definitely done something wrong here then, haven't I?
Wouldn't have 9 become wait, hold up.
Oh, because it was k minus 9, not plus 9.
Shouldn't it have
I
been,
wrote it
yeah,
down.
plus 9.
Yeah. So it should have started at k minus 9. That will make it plus 9. Which, yeah, okay. I did all my negatives as positives, apparently. Yay me. Okay. Cool. That's going to make a lot more sense now. K's cancel. -1, -1, -7 makes -9, and then this whole thing goes to 0. That's better. Yeah, so even though there's a k in there, we can see that we don't really care what the thing says. We just need to identify it as a polynomial. And because we identify a keyword divisible, we know factor theorem is going to be a thing that matters for this.
Right. Alright, so I guess like what happens is every time I see like something other than x's, I just like panic and forget about
Okay.
the theorems.
Yeah, I mean, I guess I'll point out, like, did you still notice it as a cubic, or did you start thinking of it as like some other weird nonsense?
No, like I still know it's a cubic, but I
Mm.
just like I look at the k minus ones and k minus nines and
Yeah.
yeah.
Yeah, okay. I mean, that's definitely something you're going to have to eventually get over. Like, the thing I'll highlight there once again is like, just figure out, hey, what type of function do I even have? And you were able to spot that. You know it was a cubic. So just focus on, okay, I don't really care what that thing says. I just know it's a cubic. And so whatever cubic methods I know of to solve things, I'm going to try and use. It's going to be a very common thing in tech active, where they're going to give you something ridiculous in the in the extended response. I don't know if you spent much time looking at the extended responses in the tech actives beyond our classes, but there are some really nasty things where it's like, here's a natural log of some massive polynomial with a division and plus minus k, and there's a whole bunch of shit in there that you'll have to just boil down to like, oh, I've got a log. That's it, really.
All right.
But okay, cool. So let's see if we can further expand on that. Find the value of k for which the expression has a remainder of 12 when divided by this. Based on what we were discussing, what do you feel like is going to be appropriate here?
All we have to do is remainder theorem.
Yeah, remainder theorem, absolutely. How are we going to use remainder theorem in this instance?
Could you say that again? You just cut out.
Oh, I cut out. How would you use remainder theorem in this instance then?
Um, so do we sub in like do we do f of 15?
Where's 15? Maybe it's zoomed out a bit far.
Oh, wait, hold on. F of 12, sorry.
Not quite f of 12 because 12 is the remainder. Remember what goes in the brackets of your what went in the brackets of our function last time?
Oh, I mean negative b on a, so
Yeah, that's it. So
f of 2.
yeah, so f of 2 in this case. So f of 2 is what we're doing, and what are we expecting?
12.
Yeah, f of 2 equals 12. So as long as we can show f of 2 equals 12, we'll be well, sorry, I guess it's as long as we solve for k such that this equals 12, we'll be sorted. So yeah, once again, I'm just going to now plug everything in. So we're going to have 2 cubed plus k minus 1, 2 squared, so 4, plus k minus 9 times x, so 2, and then minus 7. That's going to equal 12. This is probably going to be linear. Let's find out. 2 cubed is 8. I'm going to have then 4k minus 4 plus 2k minus 18 minus 7 equals 12. And that's just linear. I mean, we can take this all the way to the end, but do you feel like that's sort of fair enough?
Yes.
Cool. Okay. Next up. So polynomial that's got some a's and b's in it this time has a factor when f is divided by x minus 2, remainder is 15. So again, we got a very similar thing. When f is divided by x minus 2, we had remainder 12. Now we got remainder 15. Same shit. A lot more open-ended this time, though. It just says calculate a and b. What do you think?
I feel like this might involve some sort of simultaneous.
That's a very good intuition, yeah. 2 variables, 2 unknowns should mean 2 equations. Nice. I feel like you're pretty certain on at least one of the equations that's going to come up.
Yeah, well, f of 2 is equal to 15, and
Yep.
the other one is, I think, f of negative 3 will equal to 0.
F of negative 3 equals 0. Yeah, because it's a factor. Nice. F of negative 3 equals 0. That'll once again just be a linear simultaneous. We can do it. It'll take some time. What do you think?
No,
Yeah.
yeah.
Okay.
Oh,
So we're going to have the values a and b in that case. Let me just pop the answer so we can have that. In the meantime, have a think about what you might do for 9b. I know it might be a bit difficult without having a full polynomial, but again, just sort of go back to, hey, it's a cubic, treat it like a cubic. So just, yeah, suss that out while I pull up the answers for this one. In fact, is that going to block everything? It did not. Nice. All right, so we had a equals 3 and b equals 8 for that.
okay. I mean, I guess there's two approaches to this. You can either divide by, like, you can divide the whole polynomial by x plus 3,
Mm-hmm.
or we can look at the constant term, and the only factor is going to be plus minus 3 and plus minus 1.
Yeah.
And then you can just try trial and error until you get 0.
Yeah, it's going to be, in fact, well, hang on, actually. There is one thing I
Oh,
didn't
never
quite,
mind.
yeah, I haven't actually brought that up today. Yeah, when you have a coefficient at the front here, there is one other issue that comes with that, which is the, what's it called, rational root theorem. So now you're essentially doing still plus minus these factors, but this is now your a term, right? You're doing plus minus of these factors as your a term. Now, obviously,
Right.
plus and minus 1 are going to count in that, But whenever you divide by plus or minus 1, you get an integer again. So we pretty much ignore the 1 factors in this case. Granted, you know, you could now still belt those out. There's only one other, well, I say there's only 2 other things to test, but that does, it's counting methods. You've now got plus minus 1, plus minus 3, and then plus minus 2 over here. The multiplication principle of those does add up. But you're right, those are the 2 ways of going about it. Just do a division here, that gets you a quadratic, which is a lot easier to work with. Or you could belt out a bunch of rational root theorems and just get them all by brute force.
Yeah.
Any of those you want to explore in handwriting, or is it fair enough on the approach?
No, it's fair enough.
Cool. This is the same question. I guess the only thing you have to keep in mind is the way this is worded. So what do you think the 2 equations are going to be in this case?
X remains of -8 and 10 when divided by. Okay. So we're gonna have f of 3 on 2 is equal to -8.
Yes.
And what's it called? F of 3 is equal to 10.
Yeah, that's right. Good order. Another thing that might look a bit challenging, find the remainder. Actually, no, it's not, because this is still just remainder theorem. We don't need to polynomial divide, so it is still just going to be f of 2, which is chill. A slightly different wording of it, prove that they're not factors. What do you think is involved in proving that they're not factors?
So for x minus 1, you'd want to sub 1 into the equation, and then if it doesn't equal to 0, then it's not a factor.
Yep, that's it. And obviously going to be the same thing for x plus 1 as well. Cool. Yeah. Okay, that's that. Now this one I remember being quite challenging, 12. P of x can be written to look like this. Q is a polynomial, A and B are some constants. The hence or otherwise part, obviously implying that the previous answer may be useful, like knowing that these aren't factors may be useful for this. Find the remainder when P of x is divided by x squared take 1.
So that kind of just confirms that x minus 1 and x plus 1 are factors, I guess.
Does it?
Because if it can be written in x squared minus 1, wouldn't that mean that they have to be factors?
Well, have a look at the overall form of the polynomial.
Oh, okay, never mind.
Yeah. If it's a sequence of products, then yeah, absolutely. If it's not so much.
Well, then we just wouldn't we want to just reduce p of x by first dividing by x minus 1 and then dividing by x plus 1? Or actually, we can just divide it fully by x squared minus 1 as well.
Yeah, that'll be a lot faster there. Correct, yeah. And so that will, yeah, what's that going to get us? Because that's a lot of arithmetic there. I'm trying to think if there's I remember there being a nice nuanced way of doing this. Because, we're not technically making use of the fact that these aren't factors in this case, the hence portion of this. What did it have to do with? Neither of these being factors. I mean, there was definitely something related to this bit here, right? The x squared take 1 being the product of these 2 things. Squared take 1, q of x. Yeah. I'd have to think on that a bit harder, but what you're describing is perfectly fine. Right, just going through and doing the quadratic. I mean, even the quadratic isn't that bad. Like, if we look at how quadratic poly division works, it's actually quite fast. It's just a bit disjointed almost, because when you're counting them down, you're doing the divisions, it's going down by 2 every single time. And so when you put your thing under the bottom, you would either have to offset this over here so you can work in nice, neat vertical lines, or just remember, hey, This is an x squared, this is an x, they can't combine. So the x squared drops down, whereas this is going to minus into each other. And so this is kind of like what we would see. This is a cubic instead of a power of 5, and there's a lot fewer steps involved. You're going to be left with some linear at the end. Because we're left with some linear at the end, what do you think we're going to therefore do to solve A and B?
Is it just like compare to the remainder?
Yeah, yeah, precisely. In fact, I just realized it doesn't even say find A and B, it just says find the remainder. So that would have just been the answer anyway. But yeah, if you did have A and B, you'd be like, okay, negative 15 is A, negative 25 is B. Cool.
And what's the Q of X thingy? Q
Um,
of X.
yeah, I mean, it's just going to be whatever the quotient is at top. So it would be this in this example.
Because basically anything is a polynomial, right? Even if it's like degree
Yeah,
of.
yeah, degree 1 polynomial. Yeah, linear.
Does that even like include like negative degrees, so, like the hyperbolas and stuff? Are they also like polynomials?
Good question.
Like x plus
Um,
one is the power negative one.
yeah, I mean, I'm inclined to say no, but it might actually have it in here. Language of polynomials. Polynomial can be written here. N is an element of the natural numbers including 0, so no, can't go into negatives. You could even have 0 though, that's really weird. So a a horizontal line is a polynomial, but nothing negative.
It's called y equal one.
Yeah, like a 1 is a 0 polynomial. Nice.
Interesting.
Hey, look at that, I did get it right. Monic polynomial, leading term coefficient O1. Nice. Yeah, yeah. I mean, it made sense. They had different names. They behave very differently to the rest of the polynomials. Obviously, they got asymptotes and all sorts of different behaviors. So it makes sense why they'd be their own sort of category.
Yeah, fair enough.
Okay, where do we go? That was that one. Cool. That we've already basically answered. This is just a slightly harder version because now you got roots. Hence, write down one, find a second. Yep, same thing, same wording. This is probably not what we were looking for. Out of curiosity, like what kind of factorization method seems appropriate here?
I guess just going like left to right and trying to find the biggest like number that fits into them.
Yeah, I mean, that'll only get you so far here. Like 8 and 27 don't really, yeah, bit tough. There's something about, if I just sort of scroll out a little bit, if you just look at the format of all of these, you'll notice some parallels perhaps.
Oh, they all have this. They're all to the power of three.
Yeah, everything's got a power of 3 in there basically. There's a specific factorization technique that is revolved around power of 3 terms. Any idea what was going on there?
No, not really.
That's fine. Yeah, it's pretty niche. We don't really use it a whole lot. It's the sum and difference of cubes. So, not entirely necessary. This is still a cubic, and so you can use factor theorem to factorize it down. Now, this actually has a lot of applications in Spech, oddly enough, because when you think about how you would solve this kind of polynomial, like finding the factor of the polynomial, that's pretty chill because you just knock this thing to the right hand side and then cube both sides of the equation, done and dusted. But because in Spech you're going to have complex numbers, it's good to understand that hey, you can actually factorize a difference of cubes type cubic using this, and you notice there's a quadratic term in there, which may or may not have complex numbers in it as a solution. I love this term, by the way, relatively prime. It's close enough to being prime. In fact, now I'm curious, what was even going on here? A and B integers, highest common factor. Alpha and beta is 1. Yeah, okay. I don't know why they made this like definition so complicated. It really was just divide the factors of the leading term by the factors of the lagging term. That's just more rational root theorem. This might be interesting. Question 20. You got P and Q in two separate quartics. They have a common factor x minus 2. Maybe not that unique. Maybe have a stab at it anyway.
All right.
That's all going fair enough.
Yeah, I got P is equal to 1, and I'm just
Yeah,
gonna sub back into my Q.
easy. For those watching the recording, that's 2. In fact, I'll let you explain it at the end, maybe.
And Q is -6.
Yeah, sorted. Cool. Yeah, what was the approach there?
Just, I mean, first sub in 2 into both the equations.
Yeah, common
Set up,
factor.
set up simultaneous and solve.
Yeah, nothing to it. Common factor means it belongs to both, so yeah, just f of 2 on both of those. Yeah, everything else is a bit different. That's about as sophisticated as those kinds of questions are going to go. We do
Yeah.
have some time left to end the class, so I'm happy to run through something else if you like, or if you want, you can have the time back, whatever you'd rather.
That's okay. I'll look through chapter 11 of through the 3-4 book because that's what I just sort of finished with Ksenia.
Yeah,
And yeah, Maybe the chapter review. There's some
Yeah, okay. Let's suss it out.
the normal questions are okay, like the tech-free questions. I didn't find them that bad.
Yep. But Tech Active got weirder.
Tech active, honestly, like the multi-choice was pretty like hard as well. Like not crazy hard. And then the extended response is just like, yeah, I don't really understand what it says.
Okay. Um, we got limited time here. I feel like we could either I could either help you understand what external response is saying, or I could probably help you end to end on a few multis. What do you think would be more beneficial for the time?
Let me look at the questions real quick.
Yeah.
Maybe question 7 and 8.
Yep. Cool. So this is a typical case where you have an integral where you don't know what f is specifically, but you do know some known values of those integrals. And so the overall goal of this kind of question is going to be to say, okay, cool. I've got this integral that I'm trying to evaluate. What my idea is to somehow rewrite this thing that I don't know purely in terms of things that I do know. So effectively, we start with this. We want to try and split this thing up enough to where it looks like the stuff in the left-hand side. That's the overall idea. With that in mind, how do you
Wait,
think?
hold on. Just before you start, right? You see the second integral in that like question? How come like 11's on the bottom, even though it's a higher bound?
Yeah, good question. So the terminals don't necessarily have to be up or lower. There's something special about switching terminals. It does something to the integral.
Negative,
Yeah, yeah, it flips it. Flips to becoming a negative version of itself.
right?
So one thing you might want to do in that case is flip this backwards. So make it back to being lower to upper, but because that makes it easier to work with, but with the
Yeah, and then
caveat
negative
that,
points.
yeah, that's right.
Right, okay.
Cool. Okay.
Oh wait, so that just means you add the two integrals together.
Yeah, it looks like it. So -5 to 4, and then flipping this around 4 to
But
11.
it's gonna be C.
Yeah, so let's have a look. So it's 2 minus 6. Yeah, yeah, there you go.
Oh, okay. Never mind.
Sorted. So the things that I was looking for there is I've got an unknown f, but known integrals. So because I have that key information, I know, cool, I've got to take the thing that I don't know, split it up into things that I do know. If you want to see a bunch of examples of that, that'll be in the lecture notes under calculus, apps of maybe not apps actually, fundamentals, definite. Let's have a suss. Yeah, that's all this shit here. So I've got 6 key examples of like, okay, here's if you have different terminals. Here's if you have coefficients. And it's like, again, got 2 things of f, 1 thing that I don't know. I've got, well, in this case, 1 thing of f, 1 that I don't know. There's a whole bunch of examples in the definite integral doc specifically.
Right.
That's that one. And where were we? It was this and then this. Cool. So as far as what's going on here, we have a diff. We have a point on the diff. We have a point on the original. And then I just want to know what happens if I sub x into the original. Okay. So, that's your key information. You've got diff. You've got some key diff points and original function points. Remember, diff being dy, and then original is always y. And then this is worded a bit weirdly. When x equals 2, y equals what? There should probably be a question mark there, but I guess that's fine. Or at least saying what does y equal? It's basically saying if I sub x equals 2 into the original function, what do I actually get? That's what it's asking. With that in mind, how do you propose we're going to go about getting there?
I mean, to get the original, we just want to like integrate the diff.
Yeah, anti-diff, that's going to be sorted. That'll be a fairly chill thing. Once we anti-diff it, what are we going to do from there?
But then we just sub in 2 in the x.
Okay. If you sub in 2 in the x, you're going to have a few complications. You're going to have an a that's still in there, and you're going to have a plus c from the integral. So
Or
none of these have a and c in them. We're not using any of this information yet. Now could we start making use of that?
I guess we start like putting in those like points and stuff to find that like full equation
Yeah,
for the
absolutely. So, we've got one that's pretty chill. Like before we do our integral, we'll notice that there's actually only one unknown left in here, and we do have an x point and a diff point. We have x equals 0 and dy dx is 5. So we can actually use that to solve our a pretty quickly, since a is the only thing in the diff equation. 5 equals a e to the negative 0, so that's just gone. 5 equals a plus 2, a equals 3.
Yeah.
Now for the integral, obviously you're going to put a plus c in there. What are we going to do to get the c out of it?
So we just used x equals 0, and
Mhm.
we can just do that again.
Yeah, we can sub in x equals 0 again. That's not the entire extent of it, but a part of it for sure.
And then hold on. When x is equal to 0, the diff is equal to 5, and y is equal to 1.
Mm.
And can't we just put in 1,
Yeah,
the
certainly.
y,
That's exactly right.
and then c is equal to 4?
That's it. Got the a, got the c. And now we're happy to sub in x equals 2 into this, because now we're going to get one of those answers. Sweet.
Yeah.
Okay. Still time. Let's. I mean, these do look a bit different. I just realized we did all this by hand, which, I mean, it's fine. Yeah, being tech active, you'd probably want to anti-diff this manually or by CAS, just so you don't mess it up. That, and it's faster, ever so slightly.
Yeah.
Oh, I just realized there's even more down here, actually. These are trapezoidal rule stuff. Yeah, any of that.
Also, you know how like so some like questions like ask for total area, some questions ask like signed area. Just to confirm, is like signed area like so anything that's underneath the like x-axis, does that become like negative?
Correct. Yeah. So signed area is the only time. Well, let's clarify that. Doing a definite integral or signed area is the only time you ever consider positive or negative area. Anything else like total, like bound, any of those other keywords that they use around area that's not signed, you consider that to be the addition of the two. So in this case, total area, you want to make this a positive. You want to consider it all being positive. It's only the keyword signed area where you want these to. I mean, these will just cancel out. If it's positive, negative, it'll cancel out.
So signed would just mean 0.
Yeah, signed would mean 0 in this case, and obviously you can see that's just not on the list here. So that's, I guess, another way. If you do somehow forget that in the middle of a SAC or an exam, if it's a multi, you can be like, okay, well, 0 is just not on the board anyway, so total must mean adding the two things together. So yeah, the only time there's ever going to be area mentioned, signed only means the positive negative stuff. Everything else, you flip negatives to positives. The reason I threw in definite integrals in there is because that's what you're technically doing with a definite integral. Definite integrals by their nature are signed. But usually if you're told solve a definite integral, they're not necessarily saying solve signed area. It's just the wording around it that's different rather than what you're actually doing. They mean the same thing, but phrased differently.
Right.
Cool. Okay. So I guess the extendeds here will be Ksenia's job. I'm hoping the rest of these are now fairly chill. And yeah, like I feel like you've got these as long as you're I guess framed in the right way of solving them. It or at least told maybe the key indicators. You get it pretty quick, which is good to see.
Yeah.
But cool. So if you're still wanting to practice a few more of those, that's the definite integral doc. That's where to find that in the.
Where do we find these things?
Oh, wait, you haven't spotted these.
And I remember I used to use these like your notes thing, and then I don't know, like one day I just like couldn't find it anymore.
Well, they're in the classroom of the school. Have you been in there for a while?
Let me open up that real quick.
Yeah, definitely double check that.
Classroom, and then do we click on like Mastermind Premium?
No, just scroll down more.
Yep.
Is
I
there?
see MISC resources.
Oh,
Miscellaneous
do you not see
resources.
anything else in there?
Exam solutions, miscellaneous resources, practice hacks, pseudocode,
Yeah,
probability,
all that. Yeah, that's what you're looking for.
functions and relations.
So hop in the calculus
Oh
bit.
wait, okay, yeah, yeah. Then there's a PDF underneath the videos. All right.
Yeah, there's a PDF and all. Oh, okay. Right, you were looking for the PDFs, not the videos. Yeah, they're all attached to the videos. Correct.
Yeah, yeah, okay, cool. No, I watched the videos. The videos are helpful.
Nice. Yeah, I'm glad to hear that. It's good to see. Cool. But yeah, there's always a PDF version on each of those. So it's under calculus and fundamentals, document 3, definite
Right.
integral.
Okay.
Cool. All right.
Cool.
Reach out if you have any questions. Otherwise, yeah, I guess maybe let Ksenia know for the next class. It'll be, I guess, clarifying those extended responses.
Yeah.
Sweet.
Cool. Thank you very much.
No, happy to help. Take care.